Hello everyone. We'll be beginning with the chapter. We'll be continuing with the chapter Gaseous Law and Thermodynamics. And in the previous lectures, we have discussed various concepts like what are ideal gases and what is the kinetic theory of gases, how the molecules interact with each other, and how does they result in the various gaseous laws. Now we will begin with the other part of the chapter, that is thermodynamics, and we'll discuss some various concepts like temperature, what is heat energy, and what are the various laws of thermodynamics and how they govern the behavior of various gases and the various processes that take place in the environment. Okay, so let's begin with the first concept, that is temperature. We very loosely talk about this term in normal life, so let's first of all make it clear what is meant by temperature. So it is defined as that thermal property. Thermal means something related to heat. That thermal property which attains the same value for all bodies placed in contact, in thermal contact, that is, they might not be even in actual contact, but they are somehow able to interact in the terms of heat energy with each other. So it is basically the property that becomes constant when A and B, let's suppose they are in thermal contact. So let's suppose they are connected by a conducting rod. Okay, which conducts the heat from A to B or B to A. So at equilibrium, at final state, the property that holds same for both these A and B is basically known as temperature. Okay, so that's why we are able to have a clear-cut notion of what is known as temperature. So according to this, the common value attained, we have scaled the temperatures in various scale like Kelvin scale, degree Celsius scale, degree Fahrenheit scale. Okay, these are the measurements of this temperature. This are just basically, we have denoted like in the form of natural numbers. When we have 0, 1, 2, 3, 4, we had denoted them to certain things. In the similar value, in a similar way, we have denoted Kelvin, degree Celsius and degree Fahrenheit for the various temperatures. Now the second thing that is very important for us to understand is what is heat energy. Okay, so basically the transfer or flow of, it is the transfer or flow of internal energy. Internal energy caused due to difference in temperature. Difference in temperature between two bodies. Okay, so this is basically known as the heat energy. Whenever there is a hotter body, let's suppose A and let's suppose B, and they are put in thermal contact with each other, so we are assuming that the temperature of A is greater than temperature of B. So which means that the energy flow would be from A to B. But this we are dealing with is basically the net flow. There might be particles or the heat energy flowing from A to B as well as from B to A. But the net flow is in the direction of A to B. So when we say that A and B are at equilibrium, that is TA is equal to TB, this doesn't mean that the energy is not flowing, that everything is constant. It is not so, because the particles are continuously vibrating and energy is flowing from A to B as well as B to A. But the net effect is 0. That is, the energy flowing from A to B is equal to the energy flowing back from B to A. Okay, so heat energy is basically the transfer of internal energy that is in the form of molecular interactions that is present. That flow of that internal energy caused due to difference in temperature, because whenever there is a difference in temperature, the energy of the molecules are different. As we learned in the previous lectures as well, the energy of the particle is given by 3/2 kT, of a gaseous molecule. So due to that, there is a difference in the energy stored in the particle. So that's why it is imparted to the other particle, because there is a difference in them. Okay. Now let's try and understand the first law of, or we call it Zeroth Law of thermodynamics. It states very basic thing, but it is the basis of the definition, or it is the basis on which your temperature scales, like the Kelvin scale or the degree scale or the Fahrenheit scale, are based upon. It says that if two bodies, A and B, are in thermal equilibrium, with another body, C, then they are also in thermal equilibrium with body with themselves. Okay, so this is basically saying that if there is an object A, it is in thermal contact with object C, and it is also in thermal contact with B, which is equivalent to saying that A is in thermal contact or thermal equilibrium with B, because ultimately the body would attain a thermal equilibrium. So this is saying this, that A and C are in thermal equilibrium and C and B are in thermal equilibrium. That is, the temperature of A is equals to temperature of C, and temperature C is equals to temperature B. Therefore, temperature A equals temperature B. And here also the same thing is achieved. So this is the basis of the definition of being what is meant by temperature, that, or the definition of the various scales that you know, of like the degree Fahrenheit, degree Celsius, because they are also defined in the form of, like the integers are defined. How the integers were defined? It was known that, say, 1 x is equal to 2 and y is also equals to 2. So x equals to y. So this is the basis of what is known as the uniformity in the natural numbers that we know. That yes, there is a natural number known as 0, 1, 2, 3, because there is a uniqueness property that if two things are equal to the same number, then they are equal. And that is maintained by the Zeroth Law of thermodynamics. Okay. So this is the very important law, which is not given that importance in actual life, but it is the very basis of defining the temperature and the things we know. So let's define what is a thermodynamical system first of all. Before beginning with thermodynamics itself, what is a system? Thermodynamical system is nothing but a collection of an extremely large amount, extremely large number of atoms or molecules, so that they together have a pressure denoted by P, a volume denoted by V, a temperature defined by T. So it is basically nothing but a huge collection of atoms or molecules which have a togetherness in them and have a unique temperature, volume and pressure defined for itself. Okay. So what can be the examples of this thermodynamical system? Like a gas. A gas has a definite temperature, pressure and volume attained whenever it's kept in something. So other example could be vapors, steam, etc. So these are kind of thermodynamical systems we are dealing with. Okay, so let's try to define a model, a working model that we want to study first of all, before doing anything else. So a very important and understanding model that is available in the various studies about thermodynamics is the piston container model. Okay, so let's suppose there is a container with us. Okay, and there is a piston overhead, and it's a frictionless piston. It can move without friction. This is our piston overhead, and our thermodynamical system would be over here. Okay, and we are typically dealing with just the gases, one type of thermodynamical system. So the gas is present over here in the enclosed space. So a very important property over here is there is no friction over here. So it's a frictionless and massless piston. Okay, so it's just as in staying there just to keep the volume fixed. That's the logic. Okay, and now there's the gas over here. There are various gas molecules over here. So obviously this gas exerts some pressure in all directions. There would be equal pressure, and there would be some temperature attributed to this gas, and the volume you can very easily calculate if you know the area of the base of the container and the height of this. So you can clearly say that volume is equal to AH. Okay, so this qualifies the definition of it being a thermodynamical system, because it has a certain pressure, it has a temperature, and it has a volume. Okay, now let's try and define what is the work done by a gas. Okay, but first of all, we are dealing with a process. Let's define what is a process. Okay, process is nothing but a collection of states. A collection of states of the thermodynamical system. As in we see that, let the gas expand. Okay, so this is a process. Example, we say that expansion of gas. During this expansion, we can have infinite time instances. We can take the snapshot of the this piston arrangement, piston container arrangement, and we can see that at each state we can define the volume, pressure, and the temperature of the gas. And this whole, through this whole transition, that is the expansion of the gas, we can have infinite timestamps, and we can get a whole process out of it, that yes, the gas expanded with these attributes to the final position. So this is basically a process, a change in the state of the gas, and it is passing through infinitely small, infinite timestamps, like a very small transition to achieve the complete transition. Okay, so this is basically the process. So we are considering this only process, the expansion of a gas. Okay, and we are interested in finding what is the work done in the expression, work done by the gas. How much work is done by the gas in expanding from a certain volume to a certain volume. Okay, so let's suppose in this piston, let's draw it again. We have that this is the container and this is the piston we have. So initially the volume was V1. The gas was exerting some pressure, and finally it reached a situation that the piston moved up, suppose. Then only it can have been under expansion, and still there was some pressure exerted over here, and we attained a volume V2. So this we are dealing with. Okay, So we want to find the work done. So first of all, we know that there is a pressure P applied by the gas, and we have the base area as A. The area of the container will be the same as the area of the piston, correct? So we are dealing with the force. Let's try and find the force exerted by the gas on the piston, which is nothing but pressure into area. Okay. Now, how has the volume been changed? The area has still remained same, just the height has been increased. Okay. So we can say that, let's suppose this height was x earlier or h earlier. Now it has h1. Now it has become h2. So we know that v1 is equal to a into h1 and v2 is equal to a into h2. Okay. So basically the piston has moved in the upwards direction by piston movement is equal to h2 minus h1. So basically there has been displacement for the piston in the upward direction. One thing is very important in this process is these are reversible processes. Okay. These all are reversible processes we are dealing with, in which these are the processes which take infinite time. I'm not giving you the formal definition, but I'm giving you the essence of what is meant by the reversible process. There's a process which takes infinite time, and the change in the state is taken through infinitely small steps. Okay. What do I mean by this is, it's not that the piston was all of a sudden jumped from V1 to V2. It was taken very slowly in infinitely small steps, increasing the height by dx, and continuously doing that until infinite time, such that the h1 becomes h2. So it's not a sudden jump of the height of the piston from h1 to h2. It is taken through infinitely small steps. This is done because whenever you take a gas from a state to another, you try to take, because if you first directly jump the piston from one location to another, the volume has all of a sudden increased, which makes this an irreversible process, and the states of the gaseous molecules is not perfectly defined, because there is a sudden change in the state of the gas. So the temperature, pressure and volume is not perfectly defined. So we want to ensure that at each and every moment of the process, all the three components or all the three properties of the gas are completely and precisely defined. So that's why we take it through very small steps and take infinite time to reach the goal. Okay. So basically, in small steps, we try to reach the goal. Okay. So basically, that is, we are saying that we are not changing the volume all of a sudden. So there is for the very infinitely small step, we have a change in the volume dV. Okay. So that is nothing but A into dx. Correct? That is the change in the volume. Now we were dealing with there was a slight change in the height of the piston. So there was this small increase in the volume. Now how much work is done? Work is nothing but force into displacement. Okay. So that is nothing but the force exerted was P into A, and the displacement is nothing but dx for a very small step. So dW is nothing but PA dx. And now we see that dW could be represented as A into dx is nothing but dV. So the work done is pressure into change in the volume. Okay. So if we integrate on both these sides, we get as dW integration on the left side is equal to PdV, this is second state and first state, PdV integrated from V1 to V2. So work in the final state minus work in the initial state is given that P into V2 minus V1. Okay. So I have loosely written this term as W2 minus W1. Basically there is no such quantity as W1 and W2. This I have just written for the sake of those who commit this kind of mistakes, because work in the thermodynamical system is defined for just a process. For a given state there is no term known as work, because work is done only when there is a process. So we don't write it in this form, this is a wrong notation. We write it as delta W, or work as simple work as P into V2 minus V1. Okay. And as we know that we are dealing with the gaseous systems, we have this as work as PV2 minus PV1. Correct? This is nothing but nRT2 minus nRT1. So this is nothing but nRT2 minus T1. Work is nothing but nR delta T. There is just one thing to care about over here, is the assumption is that the pressure is constant. Otherwise we won't have been able to take P out of this picture over here. We took P out, that's why we were able to integrate very simply and just write it as V2 minus V1. Okay, so this is the work done in the case of a gas expanding under the condition that the pressure is constant. Okay, as I told you, we try to expand the gas in infinitely small steps and try to take it to the final state. And we do so because we want that at each and every state the pressure, volume and temperature of the gas is perfectly defined. This we do because we might need to plot the graph of the state of the gas at various instants throughout the process. So there is a very important curve, PV curve, that we draw for the gas. Okay. So while the gas was going throughout the process, we plotted very small we took very small steps, and at each instance we tried and plotted the temperature and pressure of the gas, and then we joined the whole curve and we get the full curve as a PV curve. So this was a condition when P was somewhat in the starting condition, PV1, PV2. Okay. So this is a typical type of curve that you would form for the process that we did. So in this thing, one thing is you must be careful. Basically you must know that what is the area under the curve. Area under any curve is given by y dx integration, or we can say fx dx, the integration of this. So here we can see that if you take the area under this curve, that is this part, this is nothing but pressure plotted into dV integral of this. And as we learned right now, that integral of pdV is nothing but the work. So the area under the PV curve gives us the work done in the process by the gas. And this is true for each and every graph, each and every process. The PV graph basically gives the area under the PV graph of the gas for the process, gives us the work done by the gas in that process. Okay. So in this lecture, we basically learned very fundamental concepts of thermodynamics, the first thing we learned was the notion of temperature, what is basically defined by temperature, and what is meant by heat energy. So heat energy is basically due to the flow of energy between one state to another, and that is the flow of internal energy basically caused due to the difference in temperature of these two bodies. And then there was a very fundamental law of thermodynamics that is known as the Zeroth Law, which in turns define the notion of existence of the scales of temperature, that is the degree Celsius, Kelvin and Fahrenheit scale. Then we learned what is the thermodynamical system basically. It is nothing but a collection of extremely large number of molecules or atoms which have a constant pressure, which have a well-defined temperature, pressure and volume. Okay, and then we decided the very fundamental system that we are going to study for throughout this chapter, that is the piston container model. And this is a basic model that is used to understand the various thermodynamical processes as well as the laws that follows. Okay, so we tried to understand the first process. We defined what is basically meant by a process, and we tried to define how to deal with it. We discovered what is basically meant by the work done by a gas in a process, like the expansion of a gas under a constant pressure, and we learned the notion about what is known as the reversible process. Reversible process is a very critical concept in this chapter, and the very important thing about this is it is reversible in the sense that at each and every moment we just do a infinitely small step, and that can be very easily reverted back, and the states of the properties of the gas are well defined at each and every instance. Okay, and then we try to find the expression for the work done, and then there was a very healthy and important concept defined as the work done from a PV curve. The PV curve is basically the graph that you will come very often in these questions, and this is because the area under this curve gives us the work done by the gas. Okay, so that's all for today, and in the next lecture we will discuss the first law of thermodynamics, what is meant by the internal energy of a gas, and we will do some various specific heats of the gas available and some of the various important properties about them. So that's all.